Have you ever wondered how a tiny twist in your DNA can lead to epic battles inside your body? Well, buckle up, because today, I, Pranav with the STEM podcast, will explore sickle cell disease in all its complexities. So what exactly is the sickle cell trait? Well, a normal red blood cell inside you is round and flexible, easily moving through your body. In contrast, people with sickle cell disease have sickled blood cells, which are rigid from clumped up hemoglobin molecules. This can lead to problems such as stroke, prolonged infections, and pain crises. Yikes. Some people call the disease sickle cell anemia, as sickle cells die easily, leading to severe blood loss. This trait is most common in African and African American populations. 1 in 12 have a sickle cell allele. Now let's get into the nitty-gritty. Genetics. The sickle cell trait is caused by a mutation in both copies of the HBB gene, making it a recessive or homozygous recessive disorder. The nitrogenous base thymine replaces adenine, creating a point mutation and leading to the amino acid valine being substituted for glutamic acid in the resulting polypeptide. I know that was a lot, so what does that mean? Well, if DNA is mutated, so is the resulting hemoglobin protein, and that negatively impacts the red blood cell. That's bad news for sickle cell people. But it's not all gray skies and rainy days in sickle cell land. People with sickle cell disease, or carriers of it, so they have one mutated and one regular allele, actually have a defense against malaria, an infection carried by mosquitoes in hot tropical places. The parasites carried by vectors cannot grow in sickled cells, but grow easily in regular cells. This is likely why most people with the disease are actually in sub-Saharan Africa, Central America, or the Middle East, as malaria is common in those warmer climates. I'm sweating already. Another side note, sickle cell disease is an example of the heterozygote advantage. So people with one regular allele and one mutated allele do not experience the painful effects of the disease, but they do get some protection from malaria. That's a win-win situation in my books. Now, until recently, the only available treatment for sickle cell disease was a complete bone marrow transplant of healthy cells into an affected individual, with limited success rates. That's hard work. However, biotechnology today has created CRISPR-Cas9, an enzyme that's engineered to cut and edit the genome. Wow. Now, how does this apply to sickle cell disease? Well, I'm glad you asked. First, geneticists extract stem cells or differentiated cells from the patient. Then, Cas9, remember the enzyme I was talking about, makes a cut in the gene that controls fetal hemoglobin, which is normal hemoglobin. It's good. If the subsequent transplant works, the patient is cured, quote unquote, of sickle cell disease. This treatment cannot be labeled 100% effective, though, until all trials are complete. Sickle cell disease, affecting about 100,000 people in the US and 20 million worldwide, marks the beginning of a genetic and biotechnological revolution in society today. It challenges us, sickle cell people, and people with regular blood cells, to think deeply about the human genome and all that's yet to be discovered within it. The issues faced by those with sickle cell disease compel us to confront broader social and ethical questions as technology advances. As we move forward, let's carry these insights with us, advocating for a world where medical breakthroughs are accessible for all and where the silent battles of those with genetic disorders such as sickle cell are met with understanding and action. Thank you for joining me in this riveting episode of the STEM podcast. Podcaster Pranav, signing off.